In this question, we've been told that the discrete random variable x has the probability generating function shown. We're told that k is a positive constant and we're asked to find the value or state the value of k. First thing I'm going to do, I can quickly expand this and I can see that the probability generating function is in its standard polynomial format where each power of t is one of the outcomes and the coefficient of each t term is the probability of that outcome. So I should be able to see all the probabilities and all of the outcomes. A reminder that if we have a probability generating function and we substitute 1 for the t value, that whole expression should equal 1. It will be the sum of all of the probabilities which equal 1. So gx of 1, we get k plus 3/5, which equals 1, meaning k must be 2/5. Okay, we may well have been able to see that from the very beginning, knowing that there were 3 terms which had a probability of 1/5, leaving 2/5 for the final term. Part B asks us to determine the value of the probability of x being greater than 4. Well, to go ahead and find any probabilities, I really want to show this probability generating function in a probability distribution. Now, this is quite a simple generating function, so it should be easy to put into the probability distribution. We have all of the outcomes except for the outcome that matches k. Well, what t term is next to k? Really, it's t to the power of 0. And now this is going to help us to set up that probability distribution. So the possible values of x, 0, 2, 3, and 5, and the probabilities 2/5 and 1/5 down the line. Okay, let's go back to our question. The probability x is greater than 4. Well, we want an equals to sign in there, so the probability x is greater than or equal to 5. This is the only outcome that satisfies that, so we have an answer of 1/5. Part C asks us to use the probability generating function to calculate the mean and the variance of x. Now, no credit is going to be given if we get it from the probability distribution. We need to use the techniques that we know for the probability generating function. Okay, so the expectation of x. We can find that by differentiating the generating function and substituting 1. When we differentiate the generating function, the k term is going to disappear because of the 0, and we end up with 2/5 t plus 3/5 t squared plus t to the power of 4. Now let's go ahead and substitute a 1, and we're going to get 2/5, 3/5, and 1. We get an expectation of x of 2. Looking back to the distribution, that sounds sensible to me. 2 is in the middle region of the sample space. If we can find the expectation of x, we can also find the expectation of x squared. This time, we're going to differentiate once more and add on the original expectation of x. So, differentiating the generating function again, we're going to get 2/5 plus 6/5t plus 4t cubed. Substituting in the 1, and we get 2/5 plus 6/5 plus 4, which ends up being 28/5. Okay, these are the most important parts. I've got the first derivative of the generating function with 1 substituted in, and I've got the second derivative of the generating function with 1 substituted in. Now, a formula for the variance, one that we're very familiar with, is the expectation of x squared minus the expectation of x. That's g double dash of x plus g dash x minus g dash x all squared. All of these had 1 substituted in. All of these we found already. It's 28/5 plus 2 minus 2 squared. That leaves us with an answer of 18/5. The variance is 3.6. The variance of this probability generating function, 3.6.